Hey there, and welcome. Every single time you flip a light switch, you're actually the final step in an incredible journey that starts maybe hundreds of miles away. So today, we're going to trace that invisible path of electricity all the way from a massive power station across the country and right into your home.
It's a trip that involves some pretty mind-boggling voltages, a huge network of transformers, and a whole bunch of hidden safety features that are all designed to protect you. So, you ready to follow the path of power? Let's dive in.
You've seen them, right? Those giant towers marching across the landscape? Well, they're just one part of this colossal system. The electricity that's powering the very device you're watching this on right now started its journey at a power station, maybe in a totally different state. Let's trace it all the way back to the beginning.
Okay, our story starts right here at the generating station. This is where some form of mechanical energy, like giant turbines spinning, gets converted into electrical energy. But here's the thing, it's not quite ready for that big cross-country trip just yet.
So here's the big picture, our roadmap for this journey. You can see the power station way over on the left. The journey starts there, with power being generated at a very specific voltage. And trust me, there's a really good reason for that.
And that magic number is 11,000 volts, or 11 kilovolts. Now, why 11 kV? Well, think of it as the perfect sweet spot. If you try to generate at a much higher voltage, you run into some serious insulation problems. But if you go lower, you have to deal with incredibly high currents, which is just not efficient. So, 11 kV, that's our starting line. But here's the catch. You just can't send 11 kV power hundreds of miles and expect it to work well. Way too much energy would just get lost as heat in the wires. To fix this, the power needs to get on what I like to call an interstate highway system for electrons. And, just like getting on a real highway, you gotta speed up.
And this is exactly how it's done. A step-up transformer takes that 11,000 volts and boosts it way up to 132,000 volts, sometimes even higher for those really long hauls. By jacking up the voltage, you lower the current, and that massively cuts down on the energy that's lost as heat. I mean, that lost energy isn't just inefficient, it's waste that costs all of us money.
So after cruising across the country on this electrical superhighway, the electricity needs to take the off-ramps to get to your town and eventually to your house. And that means the voltage has to come back down, like way down.
And this happens in stages, using a series of step-down transformers. So at a main substation, that 132 kilovolts gets dropped to 33 kilovolts for things like heavy industry. Then at an intermediate one, it's lowered again to 11 kV for lighter industry. And finally, at a city substation right near your neighborhood, it's brought all the way down to the 220 volts that all your home appliances are designed to use.
Okay, the power has officially arrived in your neighborhood. Now we're at the final and maybe most crucial steps of the journey, from that pole on your street, right through your walls and to the outlets.
So, from the local pole or an underground cable, power comes into your house on 3 separate wires. You've got the live wire, which carries the current in, you've got the neutral wire, which completes the circuit, and you've got the earth wire, a supercritical safety feature we'll talk more about in just a second. These wires pass through the company's fuse and your meter before they even get to your main switch.
Right, and this main switch is absolutely crucial. It's what's called a double pulse switch, and its job is to be the ultimate safety cutoff. When you flip it, it doesn't just cut the live wire, it cuts the neutral wire at the same time. And what that does is it completely and safely isolates your entire house from the power grid.
All right, now let's meet the real unsung heroes of this whole system, the safety devices that are hidden inside your walls. You can think of them as your personal electrical bodyguards, and they are constantly on watch.
First up is the fuse. Now, a fuse is basically a sacrificial lamb. Inside is a really thin wire made of a special alloy that has a super low melting point. You can think of it as a one-time use version of the circuit breakers in most modern homes. If the current gets too high, that little wire instantly heats up, melts, and breaks the circuit before your expensive TV gets fried.
Now here's where things get really interesting. Where you put that fuse is everything. It must go on the live wire. Take a look at the diagram on the left. When that fuse blows, the appliance is totally dead, completely cut off. But now look at the right. If the fuse is on the neutral wire, even when it blows, the appliance is still connected to that high-potential live wire, and that makes it incredibly dangerous to touch.
And you know what? The exact same logic applies to your light switches. A switch must always break the live wire. If it's on the neutral wire, sure, flipping the switch will turn the light off, but the entire light fixture is still live, still at a high potential. This is super deceptive and creates a serious shock hazard if you go to, say, change the light bulb.
And finally, we have the earth wire. This is your ultimate protection against getting shocked by a faulty appliance. If a live wire inside something accidentally touches the metal casing, the earth wire gives that massive surge of current a super easy, low-resistance path to flow safely into the ground, instead of through you. And that usually trips a fuse or a circuit breaker in the process.
We're almost there. The journey is nearly complete. The absolute final point of contact between this gigantic, continent-spanning grid and your device is the humble wall plug.
Have you ever wondered why that top pin, the earth pin, is a little bit longer and thicker than the other two? Well, it's actually a brilliant piece of safety design. Because it's longer, it makes that safety earth connection first when you plug it in, and it's the very last thing to disconnect when you pull it out. This makes sure the safety system is always engaged before any power starts to flow.
And of course, to make sure everything gets hooked up correctly, the wires themselves are color-coded. The old standard used to be red for live, black for neutral, and green for earth. But the new international standard is brown for live, light blue for neutral, and green and yellow for earth. Standardization like this is absolutely key for safety.
So after this entire journey, it really all comes down to avoiding two main dangers: fire, which is caused by overheating wires, and of course, electric shock. Every single system we've just talked about is designed specifically to prevent these two things from happening.
So what's the takeaway for you? Really, it's about respecting the system. Always use the properly rated wires and fuses for the job. Never, ever handle switches or plugs with wet hands. And make sure your appliances are properly earthed. Following these simple rules is your way of working with this entire amazing safety system we've just explored.
From 132,000 volts soaring across a transmission tower, all the way down to the carefully controlled power right there in your home, it's a truly amazing journey. Now that you understand the complex path electricity takes, it kind of makes you wonder, what other invisible networks are all around us, just powering our world, waiting to be explored?